So hello everyone and welcome back to this next lecture in the DC to DC converter series, and we have been trying to simulate a transformer. So this is where we had left off, where we were writing the transformer model control file. So before I start this lecture, as usual, a little bit of background that if you are interested in these kind of video lectures but you would like something a little more comprehensive as a full-length course, I do have some online full-length courses on the MOOC website Udemy, which are complete courses on power electronics and using Python in power electronics. So this is the first course, which is simulating power electronic circuits using Python. In this I talk about the basics of Python power electronics, how to install the software, some basic power electronics, and a case study of simulating a buck converter. If you are interested more on the signal processing side, then I do have another course which is called Basics of Digital Signal Processing for Power Engineers. In this I talk about how you can design filters for power engineering applications. So I have some basics of signal processing, the installation of Python and some basic tutorials on NumPy and some of the other tools used, and finally there is a case study of designing a low pass and notch filter using frequency response characteristics. And the last and the most recent course is simulation of magnetics for power electronics using Python, and this is probably most relevant for the next few lectures. In this course I talk about how you can use Python to simulate inductors and transformers. So I go through the basics of magnetics in electrical engineering, of how you can model a magnetic element such as an inductor or a transformer, and I have a case study of a flyback converter. So if you are interested in simulating transformers and converters with transformers, check out this course. So with this background, let me go back to the simulation. So this is where we had left off, and most importantly, this is where we had left off when we were actually editing the control file. So we had come to the situation where we had to define L1 and L2, right? So as I already said, let me go back to the circuit, and the circuit is a two-winding transformer. The circuit is this part of the winding, which is the actual transformer winding, which is what we're going to model. We are modeling it as a controllable voltage source in series with the variable resistance, right? Now this is the model. Basically it's a current, it's basically a current source which is being controlled. Now in an actual transformer, this contains the winding. The winding has inductance and it has some amount of resistance as well, a winding resistance. Now besides that, the winding usually has some amount of leakage as well, because not all the flux that is produced by the winding is linked with the core and is also made available to the other winding. Some amount of the flux will also leak. So this winding will have to consider the magnetizing inductance and the leakage inductance. That will be the self-inductance of this winding, right? Whereas the mutual inductance is just the magnetizing inductance. So let me go back to the control file and let me start talking about this. So how do we define this? We go up and start writing some parameters. So let me just put a comment and say inductances. So how do we define the inductance? The inductance, the self-inductance of a winding, is typically such that the magnetizing current of a transformer is around 1%, right? Usually around 1%. So now what that means is, if I say XL1, right, is the reactance of this self-inductance, then this self-inductance is such that if V1 is the voltage applied to the winding, then I1 is the current through the winding, the rated current. Then this rated current is going to be 1%, right? So what that means is we have to multiply this by 0.01, right? Now of course we have opened up a few other issues. What is this voltage? What is this current? So for that we need to define the capacity of the transformer. So let's define that. So first thing we need the voltage rating. So let's say we have V1 and V2. So V1 is the voltage rating of the first winding or the primary winding, however you want to call it. So in our case, we are using a simple 1:1 ratio transformer with 240 volts on the primary, 240 volts on the secondary. As we go ahead, we will change this, but for now, this is a good starting point. Then, let us also define the secondary voltage. So, this is the primary and the secondary. The next thing we have to define is the capacity. Now, the capacity of a transformer is usually defined as the voltage rating, volt rating, VA rating of the transformer. So, let me call this, actually let me give this a better name because V1 can actually be misleading. It is V1 rating and V2 rating, or rather rated. That makes better, is the rated voltage, right? And here I will say VA rated. Now, for a transformer, it totally depends on the application. So we could consider, for a 240 volt transformer, we could consider a 10 kVA transformer, a 20 kVA transformer, something like that, right? So let's choose a 10,000 volt ampere rating. I'm just going to write this VA, right? This is the unit of this value, that is VA, volt amperes. So now that we have this, we can now calculate the currents. The current will be I1 rated is basically VA rated divided by V1 rated, and I2 rated, that is the rating of the secondary winding, is basically V1 rated divided by V2 rated, right? Now, this is very convenient. Now that we have these two, the question is, can we use it here? Of course we can. Now all we have to do is plug in these values. So that's what we're going to do. So if I say XL1 is equal to V1 rated divided by I1 rated, this is the inductance or the reactance of this first winding, right? So that is basically this reactance that we are choosing is such that if the voltage applied to the primary winding is equal to the rating of that winding, then only 1% of the rated current will flow through it. This is assuming that the secondary is open, right? So we are applying voltage only to one winding and leaving the secondary winding open. This is the definition of an open circuit test. This is how you define an open circuit test, and this is, in an open circuit test, is how you determine the magnetizing current of a transformer. So now that we have this, it's pretty easy to just define XL1 is divided by 2 into pi. To get pi, I'm just going to import math above. Let me import math all the way above, because pi is available there rather than me trying to write it. Math.pi into the frequency. Now the frequency, again, it's better to actually define it rather than, so I'm just going to say F rated is equal to 50. Actually, no need to define this way. F rated is equal to 50, and I'll just put a comment saying this is Hertz, right? So now that we have this, all I have to do is copy it and paste it here, right? This is my inductance. Similarly, I can do the same thing for L2 as well. Alright, so we now have L1 and L2. Now the question is, what is M12 and M21, right? Now, it's important to know what is the difference between the self-inductance and the mutual inductance. In the case of a transformer winding, the self-inductance will consist of the mutual inductance as well as the leakage inductance. So therefore, let me write this comment. L1 is equal to Lm plus LL1, where LL1 is the leakage reactance. Let me write this small, right? LL1 is the leakage inductance of this transformer. This is the amount of flux that leaks into the air and does not go in the core, right? And the same goes for the second winding also. So now the question is, how do we determine this? We determine this by a simple rule, that is, we just say how much is usually the leakage that we would like a transformer to have. Now this can be determined using experiments such as the open circuit test and the short circuit test. You can determine these things, or you can take a simple value, like you can take a 1%, usual 1% value. The 1% means that if a current equal to the rated current, right, were to flow through, actually I forgot something, I have to define XL2. XL2 was not defined, right, now it's okay. So if a current equal to the rated current were to flow through the winding, then that rated current will produce a 1% drop across this leakage inductance. That is, the drop across this leakage inductance is going to be 1% of the rated voltage, right? So let me write that down. Again, let me write XLL1, that is the reactance of this leakage is equal to such that if I1 rated were to flow through this, right, then in that case V1 rated is equal to 0.1%. Let me delete this and say 1% of the voltage rating will be produced as a voltage drop if the rated current flows through this winding. Alright, so it might be a little confusing, but just think about it this way. If I1 rated flows through this, so you just have to take this to the left hand side. If I1 rated flows through this reactance, then the drop across this reactance will be 1% of the rated voltage, right? And this is usually a reasonable value. Now, we just copy this for the other one as well. So I'm just going to copy, change the variables, I2 rated. And now that we have this, we can just define LL1 is equal to XLL1 divided by, let's copy this and paste it here. And I'm just going to copy this whole thing and paste it here. Save me some typing. LL2 is equal to XL2 by this. So now that we have these two values, how are we going to express it? Let's write the equation for LM. Alright. So LM1 is the mutual inductance of the first winding. Right. So what that means is LM1 is equal to LL1, or rather L1 minus LL1, right? That is, this is the self-inductance minus the leakage inductance is equal to the mutual inductance, right? Now, in the second case, LM2 is equal to L2 minus LL2, right? So basically, we are deducting the leakage from the self-inductance, and that is the mutual inductance, right? So these are the values that we need. So let's put it here. We know Psi1 is equal to L1 into I1. The second one will be LM2 because this is the mutual inductance of the secondary winding. Remember, this is the current flowing in the secondary winding. So we have to take into account the magnetizing current of magnetizing inductance of the secondary winding. The same goes here. We just have to say LM1 into I1, right? So these are our equations. Now, what are we actually doing here? We have calculated Psi1, Psi I1, or rather Psi1 and Psi2. These are the flux linkages. We know these. We have to now calculate I1 and I2. So this is basically a simultaneous equation, right? Now, how do we solve a simultaneous equation? It's pretty simple. We have to isolate it. Now, there are two ways. The actual rigorous way to do it is to write this in matrix form, but I will not do it in this lecture. If you want to know how to do that, it is covered in this course, right? So in this course, I do talk about how you can actually solve these equations, or in any of these, how you can solve these equations in a matrix format. I will not do this in these lecture series because it is a little longer. So instead, I'm just going to write this. I1, so all we have to do is take it on this side. So basically, Psi1 minus LM2 into I2, and this whole thing will be divided by L1. Let me just put a space. So this is what we are going to substitute in the other one, right? So let me just comment this out and let me paste it here. So basically we are going to say that I2 is equal to, take this term on this side and calculate it. So I2 is equal to psi I2 minus L M1 into I1, and I1 is this value. So let me paste it here. Divide this by L1, right? So this is this particular equation, and we are now going to divide this whole thing by L2. I mean, this is just solving equations. Now that we have this, all we have to do is copy this line here. Now again, as I say, this is not the most elegant way to solve this. The reason why I'm doing this is because this is just two equations and this is a simple way to do it. The more elegant way to do this is to solve it using matrices, right? So I won't do that here. It's in the course. Go ahead and check it out. Now that we have these two, I1, I2, the next question is, this has to be now placed back into the circuit, right? So now that we have, what are the currents that flow through this winding, right? So just a recap, we are applying a voltage. It could be to just one winding, it could be to either the primary or the secondary, or we could have voltages applied to both windings. Doesn't matter, right? In a transformer, anything can happen. Now, once the voltage is applied, we are measuring the voltage, right? We are calculating the flux linkages. So let's come back here. We are calculating the induced EMF. With the induced EMF, we are calculating the flux linkages. Using the flux linkages, we are calculating the currents. We now know that the winding currents are equal to these values. What we need to do is we need to adjust our voltage source and our resistance such that it is equal to these currents, right? This is what we have to do. Now, how are we going to do that? We already have in our simulator created these control outputs. We have created a control output for the control voltage source and for the variable resistance. So we can adjust these values in such a way that we are able to produce the required amount of current, right? Now, I will stop this lecture now because it's already getting a bit long, and I do realize that some of these lectures are long. The past one was almost 30 minutes. So I will stop this lecture now, and in the next lecture, we will now figure out how we can convert these currents, and or rather we can express these currents using controllable voltage sources and variable resistors, right? So if you have any doubts about what I did in this video, please do post in the comments or email me or message me on social media, whichever is your preference. Otherwise, I will see you next week where I will continue with this, and I'm not sure if we can finish it off in the next lecture. Maybe it may take a few more, but I would like to take my time with this because this is a slightly complicated concept. And as before, if you need more details, feel free to check out this course. In this course, I talk about everything related to magnetism, especially in electrical engineering. So go ahead and check it out if you want. So with this, I will end this lecture. Thank you so much for watching and see you soon. Goodbye for now.